So hi, our next algorithm is all pair shortest path, or we can say Floyd Warshall. Okay, so this is all we are at the end of algorithm course. So this is the last algorithm, you can say. So if we have any algorithm more, I will keep adding, but this is at the last, so no need to give up now. So this is just a last algorithm, and this is very easy. Okay, so even if a graph is present and a question is asked, it's easy. Okay, so let's start. So now, in given a graph, a graph is given. So till now we have done single pair shortest path. Okay, so difference between single pair was Dijkstra's algorithm and then Bellman-Ford. So and the difference with single pair shortest path and all pair shortest path is that single pair we have already taken a source, and from that source we have taken out whichever is the minimum path to every vertex. But here all pair shortest path is in we will do a matrix kind of thing. In that matrix, in the final matrix, you will get with any vertex to any vertex, you will get the shortest path. Okay, so this is basic difference between all pair shortest path and single source shortest path. So in name only it is quite understandable, but still we are here, so don't confuse it. Okay, so all pair shortest path means in the matrix, and the final answer you will get the minimum cost to every to any vertex to any vertex. Okay, so now our graph G is given with n vertices. The problem is to find the shortest distance between every pair of vertices. So every pair of vertices we have to take, and you have to find out the shortest distance. Okay, so the graph is represented by cost adjacency matrix. So cost adjacency matrix we have to do, and length of the shortest path between, this is between, okay, I have written BW. So between every pair of vertices is ultimately stored in n cross n matrix A. So let's see the algorithm. We will do an example. Okay, so just don't get scared or leave the video. Okay, so all pair shortest path is, this is cost, this is our matrix, and n cross n is our vertices. N number of vertices are present, and this is A is our matrix. Okay, so for I equals to 1 to n, do, so this is a for loop. I is the source vertex, so for every source vertex we will continue this. Okay, so for j equals to 1, so for every I we will take an destination. So particular I 1, so for 1 then 1 it will continue to 2. So this is just basic for inside for. Okay, so I is our source vertex, j is our destination vertex. Okay, so cost is stored in Aij. Okay, so this particular will give you a cost. So our source vertex from, let's say, this and this, so this will be, if this is our cost, so this will be stored in this Aij, the cost will be stored. And then for C, now if we have to take an intermediate vertex, so if we see, this is just, let's say there is another vertex. Okay, so like this, anything like this. Okay, so if we take another intermediate vertex, via that vertex, if we can get anything better than the previous cost. Okay, so minimum, we are trying to find out the minimum cost. So let's say k is our intermediate vertex. So for every k we will do k is equals to 1 to n, we will continue for every vertex. Okay, so for, let's take k as some intermediate vertex. So for every, like for all the vertices we will take k as the intermediate one. So for I, same way, so I is 1 to n, j to 1 to n, and if a of ij is greater than aik plus k of j, so we have broken into two cost. Okay, so previously it was stored, this cost of ij was stored as aij. So if this is greater than the broken part, so if not broken means via, we have taken see, we can go from this, let's say this is source, this is destination, we can go directly this, or you can go via this. So there is a path between this, so you can go via this, or you can take this direct path. So if this cost is, let's say this cost is 4 and this is 1 and 2, so 1 plus 2 is 3, so 3 is so 4 is greater than 3. Same way I have written, so 4 is greater than 3. Okay, so we will take this via path. So let's say this is our intermediate path. So I plus k, this is I, this is j, so I plus k, k plus j. Okay, so 1 plus 2 will give you 3, so we will assign it as the lowest value. Okay, a of ij will be written as a of ik plus a of kj. So we will replace this with this. Okay, so now this will give you the minimum path between these two vertices. Okay, so for all the vertices we have to do, and we will take each vertex as intermediate one. We will continue with this. Okay, so I don't know if this is pretty clear to you. We will take an example and we will see. And for time complexity, see, you have this 3 for loops. It will be order of n cube. Okay, so I think these questions are asked. Let me check once if this was asked n cube. I think in test series this was asked. So in GATE 1998 it was asked that which one of the following algorithm design technique is used in finding all pair shortest path. So 4 options are given: dynamic algorithm, dynamic programming, then backtracking, greedy, and divide and conquer. Okay, so DP, so dynamic programming is used in all pair shortest path. So one question was asked, I think n cube was okay, n cube was asked also. Okay, so 2013 time complexity was asked. What is the time complexity of Bell? Sorry, not here. I think some wrong is there. Okay. So no, this is not the question. This is actually asking of Bellman-Ford. Okay, so this is not the question. So this was asked in 1998, but I think this is important. Some test series have seen this question. Okay, so let's take an example. So let's take this example and find out every minimum cost between every pair. Okay, so first thing, let's say A is 0. First just write the adjacency matrix here. So 1 2 3 1 2 3. So this is a directed graph. Okay, so 1 1 will be 0, 2 2 will be 0, 3 3 will be 0, because there is no self loop present, so everything will be 0. So from 1 to 2, this is 4. Okay, so 1 2 3, this is 11. So you can write it like this. I kind of mess it out, so it's better. It's looking like a TikTok. Anyway, so now 2. So from 2 to 1, this part is there, 6. 2 to 3, this part is there, is 2. So now from 3 to 1, this part is present, which is 3, and 3 to 2, no path is present, so it is infinity. So now let's say via 1 we have to do. Let's say via 1 first. This vertex via 1 we are doing. So we have already seen we have to take some via intermediate vertex and do it out, do the example here. So let's say we are doing the first. So 1 2 3 1 2 3. Okay, so this will be always 0, and since we are using 1, so this will be remaining same only. Okay, so this will remain same. So we are using 1 and we are doing the other. Okay, so now from 2 to 3. Okay, so from 2 to 3, if we are this is previously it was 2, if we are using 1, so this is 6, then 11, so it is 6 plus 11, 11 plus 6, which is 17, which is greater than 2, so it will be remaining as 2 only. Okay, so now next is 3 to 2. So 3 to 2, previously it was infinity, anything will be less than infinity only. So 3 to 1 is 3, 3 to 1 is 3, then 1 to 2 is 4, so 3 plus 4 is 7. So 7 is obviously lesser than infinity, so 7 is put here. Okay, so now next we have to do for every vertex. So k was running from 1 to n. Okay, so for every vertices. So now if we are doing via 2, if we are going via 2, 1 2 3 1 2 3. Okay, so this will be zeros only, and via 2, since we are going via 2, this will be same only, 4 6, then this is 2. Sorry, why I am looking, so sorry, this is very important. Okay, don't look the previous pictures, don't look the first picture, look at the previous picture. We have not picture, the matrix, the previous one. Okay, always the previous matrix. So this is 4, this is 6, this is 2, and this is 7. Okay, so if you have written something infinity, it would have given you wrong answer. So now next is 1 2 3. 1 2 3 was previously 11. Okay, come here. 1 2 3 was 11. So now if we go via 2, 1 2 2 is 4, 1 2 2 is 4, and 2 2 3 is 2. So 4 plus 2 is 6. 6 is lesser than 11, so it will be 6. Okay, and now 3 2 1. 3 2 1 was 3 only. Okay, and 3 2 1, sorry, it was 3. We can check it out here. 3 2 1 was 3, and if we go via 2, okay, so 3 2 2, nothing is there. 3 2 2 we cannot go, so it will remain same. It will be remaining same only, 3. So now lastly, I have written it out so big way. So here, let me write here. Okay, so A3. Okay, so you have to go via 3. So 1 2 3, 1 1 2 3. So this will be 0 since there are no self loops. Okay, so if any self loop is present, 3 to 3, like it will be taking some value, but here there is no self loop, so you don't have to 3. So now 3, since we are going via 3, just copy it out. 3 7 6 2. You can just go via 3 also, but it will remain same only. We are already using that vertex. So now we have to do this other 2, and we have to check this with this. So 1 to 2, 1 to 2 is 4 here. If we use 3, so if we use 3, 11, and there is no path from 3 to 2, so it will remain 4. And from 2 to 1, so 2 to 1 was previously 6, 2 to 1 here, so 2 to 1 is previously 6, and if we use this 2 to 3, 2 to 3 is 2, 2 to 3 is 2, plus 3 to 1 is 3, so this is 5. So 5 is less than 6. Previously it was 6, and now it is coming as 5. So 5 is less than 6. So this is our ultimate vertex matrix. So here you can see if you just see from 2 to 3, you will get this. All pair shortest path is giving. For every pair you will get the shortest path. Okay, so this is basically very easy. Okay, so this is you can take more examples and you can trace it out. So it is really easy. It is nothing more to it. So let me check if any get question I can find out. So if you love watching my videos, please do subscribe. I am almost at the end of algorithm, and I will continue with other subjects also. Okay, so please subscribe to my channel if you love watching my videos. Okay, this will boost my confidence. So I could find this only one question from Floyd Warshall. Okay, so this was asked in GATE 2016 set 1, 2 marks question. You can read the full question. I have taken the main point here. So this diagram is not given. Okay, just this matrix, these are also not given, and the question is asked. Okay, so now the question is the largest, this is a matrix given, so the largest possible integer value of x which is at least one shortest path between some pair of vertices will contain the edge with weight x. So the basically the question, by seeing this it is hard to understand, so just put ABCD as matrix and let's put this in a graph. Okay, so this is not an directed graph, because see, this is a transpose matrix. Okay, so about all these matrices we will do in mathematics course. So for now you can see just if you just transpose it, if you do the you will get the same matrix. So this is not a directed graph, this is undirected graph. Okay, so this path has to be present. So what is the value? At least one shortest path will be present between C and D. So this is x is coming here, so this will be present. So you can see from C to D there are two paths. So C, A, D, C, then A, then D. So this is 5 and 8, this is 13. So this is giving 13, and if we take this path C, B, A, and then D, 5 plus 2 plus 2, 5 plus 5, 10 plus 2, 12. So 12. So 13 is one path, 12 is one path. So among this 12 is lowest. Okay, so answer is 12. So basically this is asking if the largest possible integer value of x which at least one shortest path will be present. So obviously this will not be taken. Between 13 and 12 will be taken. So if it is 12 and this will be giving, this CBAD is also giving 12, you can take either. Okay, so you can take the via one or you can take this path also, since it is equal, so you can take either. So 13 will not be our case, 12 will be our case. So if we take this path, it will coming as 12. So 5 plus 2 plus 5 is giving you 12. So if you put the 12 as the value of x, you can take this path also. So basically this is asking that we have to take this x path. So what can be the value of x here? So x can be value as 12. Okay, so this is a NAT question. Okay, so you have to put the answer to virtual keyboard. So we're at the end of algorithm. I hope you have loved watching my videos. If you do, please do subscribe. I will keep on adding other subjects also and in mathematics in parallel. So bye and see you in next video.